Hi everyone, this is the ninth video in the C8 rate and equilibrium topic. This video is going to look at how we use ammonia from the Haber process to produce fertilizer chemicals in labs before turning them into the fertilizer mixtures that we then use on our crops. So I'm going to start by talking a little bit about the reaction. So when we have these types of reactions, what we're going to do is we're going to actually react the ammonia with an acid, and there are three acids that you're going to need to know about, which I'm going to go through in this video. This is a neutralization reaction because what it's going to produce is an ammonium salt, and it's this ammonium salt that's going to become our fertilizer. Okay, so here's our ammonia in the middle, and ammonia will react with our three acids to produce one of each of these chemicals. So ammonia is going to start by reacting with nitric acid, which has the symbol HNO3, and it's going to produce ammonium nitrate salt, which has the symbol NH4NO3. The NH4 is the ammonium ion, okay? So that's what that one's producing. If we were to react ammonia with sulfuric acid, which is H2SO4, you would produce ammonium sulfate, which has two ammonium ions bonded to our sulfate ion, which is the SO4. And then our final acid is phosphoric acid, okay? And that has the symbol of H3PO4. Now, this is probably the first time you guys have ever met phosphoric acid. We don't use it very often in labs in schools and things like that because it's not as an effective acid for us to show you practicals with. So this tends to be used more in industry to create particular chemicals that we would need to use. We're going to use this to create ammonium phosphate because ammonium phosphate will contain two chemicals that plants require for healthy growth. And what we've got here is we've got three ammonium ions and our phosphate ion. So what I'm going to do is I'm going to quickly go through the word and symbol equations for these reactions because you're expected to know them for the exams, and then move on to how we actually produce these. So I'm going to start with our nitric acid one. So we're going to react nitric acid and ammonia, and we're going to produce ammonium nitrate from it, okay? And so if we were to write the symbol for this, we're going to have HNO3, and this is an aqueous solution, so we're going to follow it by AQ. NH3 AQ becomes NH4NO3 AQ, like so. And I'm just going to check that that's completely balanced. So the hydrogen from our nitric goes over here to make our ammonia into the ammonium. Yep, that is perfectly balanced. So that's the one for to make ammonium nitrate. So let's have a look at what happens when we make ammonium sulfate. So we're going to react sulfuric acid with our ammonia, and that's going to make ammonium sulfate. And I've just realised I'm going to run out of space. I'm just going to squash that there. So if we have our H2SO4 AQ, remember you will probably be asked to include the state symbols on these equations as well, so please remember to do that. Here is our ammonia AQ, and then that's going to become NH4 in brackets 2 SO4, and because we've got two of those, I'm going to have to stick a 2 in front here, and I'll put my AQ on the end here as well. So that's a balanced symbol equation for the reaction to produce ammonium sulfate, and the word equation for the reaction as well. And then lastly, we have our equation to create ammonium phosphate. So we're going to react phosphoric acid. I'm going to try and make sure I don't run out of space on this one, with ammonia, and that's going to make, and I've failed miserably, guys, ammonium phosphate. And then our symbol equation for this one is going to be H3PO4 AQ plus NH3AQ produces NH4 brackets 3 PO4 AQ as well. And I'm going to need to balance that again, so I'm going to stick a 3 in front of my ammonia, and that's our balanced equation for this. So each of these can be produced with the same method in a lab, and we do this in what we call batch production or small batch production, which means that we make small amounts and shut down often. So we have to shut down and clean up and then restart. It's quite labour intensive, this sort of thing, because you need a person to make it every single time. So these aren't the most efficient ways of producing fertilizers, but they are good for us for testing and things like that, okay? So how do we actually produce fertilizers in this process? Well, we're coming back to a practical that you guys should have learned previously in the triple science course, titrations. So each of these is produced via a titration. So what we're going to do is we're going to place our ammonia into a conical flask. This time, however, we're not going to add any indicator. We don't want indicator. We're going to use pH probes. Now, the reason we don't want indicator is because this is an impurity. We then would have to remove that impurity to be able to use it. So we're going to measure the pH with a pH probe. And what we're going to do is we're going to add the acid 1 centimetre cubed at a time from the burette. And after every 1 centimetre cubed, what you're going to do is you're going to swirl the mixture, and that's going to hopefully make sure that everything you've just added reacts. You're then going to either do one of two things. Now, if you use a pH probe, you're going to pop your pH probe in and measure the pH and see if it's dropped, or you could dip a glass rod into the mixture and drop the solution onto litmus paper and then check the litmus paper's colour. You will continue to do this, or you'll repeat it until the litmus just turns pink or the pH probe just reaches pH 7. Okay, guys, and that means that we've actually performed a full reaction, we've neutralized it, and then what you're going to do is you're going to aim to get your crystallized salts out of it. So to obtain your solid salt, you're going to perform crystallization using a water bath. Remember, we don't want to use just a naked Bunsen burner flame, because that's going to make it spit and things like that. A water bath will allow for the water in the mixture to evaporate off slowly, which will produce bigger crystals, but will also produce crystals at a safer rate as well. So that's how we produce them in the lab using a titration. Why are we actually doing this? We're doing this because we want to make NPK fertilizers. Now, NPK fertilizers are a formulation, okay, guys? They're a mixture of different chemicals or different chemical fertilizers, okay, guys? Now, we make the mixture the formulation depending on how much of each thing that we want. So we've got nitrogen, we've got phosphate, and we've got potassium. And that's what stands for the N, the P, and the K in our NPK fertilizers. And the reason that we've actually done this is because each of these three things is important for plant growth, especially for healthy plant growth. So our N and our P are needed in growth, okay? Especially in terms of like root growth and things like that. And the shoots, okay, guys? Our K, our potassium, actually has two different jobs within a plant. So potassium is needed to produce chlorophyll and keep the plant green. Now, you should know from biology that green plants will perform more photosynthesis, so they will have more energy, which means they'll actually grow. K is also needed for healthy flowering and fruit production. So if we're using this in order to grow crops, and we're using it on, say, land that's going to have fruit trees and stuff in it, we're going to want this potassium in there, because the whole point of growing these plants, especially if they're fruits, is to actually harvest the fruit from it. And these fertilizers are spread onto the land to replace any elements that have been used up in the soil by plants as they grow, and to also keep that level correct. Now, when we make NPK fertilizers, we make the formulation in a ratio of N to P to K. So what that basically is it's a ratio that tells you how much of each of the parts is in the mixture. And farmers will buy different NPK formulations based on what they're growing. So, for example, one that we could have is a 14 to 12 to 14 ratio. So that tells the farmer that there are 14 nitrogen molecules or compounds with nitrogen in to every 12 phosphate and 14 potassium. So if they have a particular crop that requires a lot of nitrogen and a lot more potassium than it does phosphate, they will buy that. If they want one that has more phosphate and nitrogen, they'll buy a one that has the ratio with that. Okay, so we make each of our NPK fertilizer batches to match what we think people will need for different crops as well, so we can sell it to them. Okay, guys, thank you for watching. I'll be back with the 10th and final video for this topic, which will be about how we make fertilizers in bulk in industry.